We now know that given Ax equals to B, the solutions can be consistent or inconsistent. Given that a system of equations is consistent, it means that we can find Ax equals to B. We can find the unknown variable x and make it such that it will be B. When this happens, the system is consistent, but there are two different types of solution we need to be aware of. The unique solution of x and infinite solutions of x, meaning that there is only one x, one vector of x that can solve Ax equals to B, or here infinite means that there are many sets of x and Ax will still be equals to B for different types of x. For consistent equations, remember that we can quickly determine if a system of equations is consistent by checking the rank of A versus the rank of the augmented matrix, as in the rank of A augmenting with the columns of B. And if they are the same, it means that increasing one column of A using the B vector did not change the number of independent columns. That also exactly means that B is in the column space of A. In the situation when A is the M by N matrix, if the rank of A equals to N, means that all the columns are independent, and not only that, their number of columns that are independent is equals to N. Therefore, its rank is also equals to N. And when this happens, there is only one x that will make Ax equals to B. So we call that the unique solution. That is, x is unique. Now, this can happen in a M by N matrix. Even when M is greater than N, we can still find the rank of A being only N. What it means is that the additional rows, because we have more equations that are known, had not increased any information in A. What it basically happens is that the more rows we have in M, they are simply linear combinations of the previous rows, the only N independent rows. What about for the case when the rank of A is less than N? Basically, in a short and fat matrix, for example, this is A, and M is the number of rows, and N is the number of columns, and N is big compared to M. And when we find the rank of such a matrix, the best that we can do is to get rank equals to M, the number of independent rows. And here it's very obvious that number of independent rows is definitely less than N, the number of columns. And here is the underdetermined system, as we have seen in this example here. And in an undetermined system, we can have infinite solutions. We'll see examples of that later. And finally, inconsistent equations. Remember, we said that if the rank of A is less than the rank of the augmented matrix, it means that by combining A and the columns of B, this rank has increased. It means that we have more independent column. It also means that B is not in the subspace of A. It also means that there is no combinations of A that can give B and that means this is an inconsistent system. In fact, most of the real life example is that we have inconsistent system. And we ask you to think about this. We say that by augmenting a matrix, its rank is less than A. And of course, that's not possible because basically you're increasing a column in the matrix by A dash B. And once you have increased the column, the rank will typically increase if B is not in the column space. And if B is in the column space, then rank does not increase, but it will never decrease.